Thank you to the organizers, and thank you to everybody here. As you'll probably figure out as I start talking, I'm coming at the themes of this conference from a somewhat different direction than a lot of people. So for me, this has been a very, very interesting week and experience. I've learned a lot of new stuff, heard a lot of new terms, and so I hope you'll find this of interest. Please feel free to interrupt me if you have questions about what I'm saying. So first, just a kind of a little piece of business here. A lot of what I'm going to be talking about is coming out of a collaboration with these four people whose names I don't want to write on the board repeatedly. So when I use the phrase Bjort, that stands for this collaboration with Christine Bauer, myself, Christina Osborne, Emily Reel, and Amelia Tebbe. And secondly, this is basically my plan. So I want to start by just introducing you to functor calculus, talking a little bit about its context, its origins. I want to go through a couple of examples of functor calculi to give you a feel for this topic. And then I want to make a connection to some of the material you've seen this week. So there's a very nice connection between Abelian functor calculus and Cartesian differential categories. If I have time, maybe I'll talk about some related work as well. Okay? So functor calculus is really something that grew out of the field of algebraic topology. So I'm an algebraic topologist by training who's kind of strayed or wandered into the world of category theory. And a couple of things I want to kind of emphasize about this context that we're coming from that affects the results and how we can come up with connections like this one. First of all, there's kind of a standard joke about topologists as not knowing the difference between a coffee cup and a donut. Is this a familiar? Okay, so, and maybe when I draw these things, you'll see why. Or, here's my attempt at a coffee cup. There's a donut, and to a topologist, these are the same because they're homeomorphic. But I'm really rooted in a subfield of algebraic topology called homotopy theory, and we just take things and make this worse. So to a homotopy theorist, this donut might be the same thing as like the ring on my finger here. So there's a sense that I can just take some sort of central axis in this donut and contract the substance of the donut down to that point. And that's a notion of equivalence called homotopic, and that's kind of the notion of equivalence that I tend to work with. So my point is that in the background with everything I'm doing, I'm working up to some notion of equivalence or weak equivalence that includes strong things like equality and isomorphisms, but is also much weaker and gloms together a lot of different things. The other thing I'll say about algebraic topology here is that maybe in some sense algebraic topology might, from a categorical point of view, be seen as working with functors that go from topological categories, so that look at topological objects like spaces, and maps them into nicer algebraic categories. And uses their images in these algebraic categories as a way to understand the spaces and perhaps distinguish between the spaces. And so some examples of this that you might have heard. Homotopy groups are examples of such functors, homology groups, cohomology, any homology or cohomology theory. Part of this, though, anytime you try to understand something by mapping it into another world, initially computations are easy. You take care of all the easy examples, and then you start working on the harder examples. You hit a wall, and so then you start trying to approximate things. So there's also a history of trying to approximate these topological objects in some sense to make the algebra here, once you map everything over to the algebra world, more tractable. And it's really kind of in this context that the theory of functor calculus arose. And the two examples I'm going to talk about really have as their, say, degree 1 parts classical constructions in algebraic topology. Another thing I want to say, just in terms of context and motivation, there have been many different ways in which ideas from calculus are generalized here this week. So I just want to make clear kind of our starting point from the world of functions, of real numbers. And the starting point is really the notion of a Taylor series or a Taylor polynomial. So I can talk about the nth Taylor polynomial of f. I can even give you a formula for it, which you probably already know. So I'm going to expand about 0. So it looks something like this. And from a undergraduate calculus point of view, this is nice because when I construct this, I'm really replacing the function f with a polynomial. I ask my students routinely, would you rather work with a trig function or an exponential function or a polynomial function on your exams? And they always vote for the polynomials. They're the easiest things to work with. And there's a sense in which this function is kind of the best degree n polynomial approximation. And there's also a sense of this, as you increase n, these approximations become better and better. So as n increases, at least if your function is nice and you're in the radius of convergence for that function, this is becoming a better approximation. Okay, and so it's kind of these features of calculus and Taylor polynomials that a functor calculus is seeking to capture. Yeah. So if I want to think about a functor calculus, say in very general terms, I want to maybe define it categorically. What do I need? Well, first of all, I need a context. So typically, we're going to start with two categories, A and B. We're going to look at some category of functors between them. So the objects here will be functors. Maybe not all functors, but some collection of functors, and the morphisms are natural transformations. And the categories A and B, depending on the calculus you're talking about, can be all sorts of things. But typically what you want, at least in your category B, is you want B to have some notion of weak equivalences. So formally, this might be like a wide subcategory of B that includes all the isomorphisms in B, but includes more things as well, such as these notions of homotopy or homotopic or homeomorphic for topological spaces. I will at some point be switching over to the algebra side of the story, and if I don't remember to say what our weak equivalences are there, I'll say that if we're looking at a category of chain complexes, that notion of weak equivalence can be a quasi-isomorphism. This is something that preserves, it's a morphism that preserves the homology of a chain complex, or something stronger than that is a chain homotopy equivalence, which is more along the lines of this notion of homotopic. And let's see. Consider this maybe a working definition of a functor calculus. So a calculus on this category of functors is some sort of construction or means of assigning to each object in the category a commuting tower of objects and natural transformation. So commuting, let's see, co-augmented tower. So something that looks like this. So you have your functor f, and there's a sequence of functors starting with P0, P1, Pn, so indexed by the natural numbers, going off in theory to infinity. And there's a natural transformation from f into each of these terms, and everything commutes nicely. Okay? And we want this sequence to somehow capture these essential properties I've identified for Taylor polynomials. So for example, I want the nth term in this sequence to be degree n, but I'm going to put that in quotes, because depending on your calculus, degree n can mean something very different. The first example I'm going to give you is a natural notion of degree n for homotopy theory, but is unnatural. Yeah, question?
F is actually the limit of this kind of chain.
If it's a nice functor. So yeah, so there is, if you think about the limit or the homotopy inverse limit of this tower, you can define that as a functor p infinity. And if your functor is nice, sometimes the word is analytic, then it's equivalent. But you can construct these just like you can the Taylor polynomials, even when there isn't a notion of convergence. Okay. So yeah, depending on your particular context, your particular functor calculus, degree n could mean many things. You want this to be somehow the best degree n approximation. So these natural transformations, maybe I'll call eta. And so we want eta and f to be somehow universal among natural transformations from F to degree n functors. So somehow this thing stands in the way of every other degree n functor with a natural transformation from F. And if I want to be completely honest here, this is often up to some notion of homotopy or weak equivalence.
What do you mean by eta and f?
The natural transformation,
Okay.
yeah, for that functor. Yeah. Okay. And lastly, you want somehow this, like as was asked, you really would like this tower to converge to F. Maybe you can't guarantee that, but you should at least have a sense that as you're going up the tower, you're gaining information rather than losing information. And so one way you might characterize this is by requiring that the relevant natural transformations, say from PM to PM, PNF, when m is less than or equal to n, and from PM to Pn of PMF are weak equivalences. Okay, so if you take a degree n approximation and then take its degree m approximation, where m is lower, you're really just recovering what you had at that lower degree. Yes?
Invert all the arrows and take more a coding diagram. Why is that not? Does that make any sense?
Inverting the arrows?
Everything the other side.
Is it- because this is what, so the first examples, things worked out this way. There's actually, you can actually talk about a co-calculus and reverse all the arrows. So that's another talk maybe.
But actually, it's like a differential linear logic. It's kind of reverse compared to ordinary mathematics. But
Okay.
it's the same in differential linear logic. If you have something such that when you differentiate inside it gives you 0. I mean, you have rows like this on my list. Okay. It's not. You agree?
Maybe, yeah. That's
Yeah.
okay.
Okay, so let me talk about some examples which may clarify or confuse matters. So the first example of a functor calculus is referred to as the Goodwillie calculus, or because Goodwillie's name is attached to several kinds of calculus, sometimes referred to as the calculus of homotopy functors. The context for this calculus, we're looking at functors from some sort of topological category. So originally, category of based topological spaces to itself. A modern version of this would be stated in terms of infinity categories. And the target category can be can be some other things as well. And you can vary this base spaces. You can look at spaces over a fixed space X and other variations on this. But I'll keep it simple for now. And so I should state a theorem here. So this theory of calculus of functors was developed in a series of papers by Tom Goodwillie that kind of took a while to come out, but most of the ideas were there in the 80s. They were published, there are 3 papers, Calculus 1, 2, and 3, published in 1990. I think the second one was 92, and the third one was 2003, that establish, among other things, that there is a functor calculus, so calculus satisfying those properties, those kinds of properties in this context, in which the nth stage, so the nth term in the tower for such a functor is what's called an excisive. So I'll explain that. But first,
For clarity, here A is top and B we left it unspecified.
so A is, or simplest version of this, A is top and B is top.
Oh, I see.
Yeah. But you can replace these with, say, simplicial model categories, infinity categories. This is how I learned it. OK, so what does n-excisive mean? Official definition goes something like this. Means that it takes strongly co-Cartesian n+1 cubical diagrams in your source category, so in this case, in top, to diagrams that are homotopy Cartesian diagrams. I'm not sure this makes any sense. Okay, so let me explain what this is in a case I can draw. So when n is equal to 1, a 2 cube is simply a square of objects, a square commuting diagram of objects in your source category. So this is in top. And the strongly co-Cartesian part says that this is kind of a push-out diagram. So it's not a strict push-out diagram because everything I do is up to this notion of weak equivalence, but it's a homotopy push-out diagram. So loosely speaking, up to weak equivalence, this object here is like the push-out of the other objects. And the idea is that if f is n-excisive, or 1-excisive in this case, then applying f to this diagram produces something that's a homotopy pullback. So now your diagram has the property that the initial object is, in some sense, weakly equivalent to the pullback of the rest of the diagram. And so probably for many of you in this audience, this does not seem like a reasonable definition of degree 1 for a functor. I get that. But in the context of homotopy theory, this makes a lot of sense. So one of the problems with computing homotopy groups is that this process is not excisive. And one of the things that homotopy theorists do is replace a topological space, say with its stable homotopy version, and compute stable homotopy groups instead. And stable homotopy groups are more computable. And this process has this property. So it turns something into some kind of hard problem into somehow a slightly less hard problem by doing an approximation. And there's even a sense in which you can say, there's a range in which these stable homotopy groups agree with the homotopy groups. Okay? So to kind of give you a little, I don't know, almost less intuition for this, if you take a simple example, you take the identity functor of spaces, so it takes a space X to a space X. In this world, the identity functor is not n excisive for any n. Okay, so it's really counterintuitive. The simplest functor you can think of is not a degree 1 functor. It's not even a degree n functor. And the problem is not so much the functor, it's the context. It's the fact that in the category of topological spaces, pushouts and pullbacks aren't the same. Okay? And so it's capturing that. But like I said, if I take the first approximation to this, I get what's known as the functor Q, or the stable homotopy functor. And so if this tower that you can build converges, what you have is something that's interpolating between stable homotopy theory and unstable homotopy theory. Okay, so again, from a homotopical point of view, this is quite nice. Okay. So one other thing I want to say about this calculus before I move on to the Abelian functor calculus, and perhaps to reassure you that maybe this isn't unreasonable, if you look at what are called the layers in this tower, so DNF represents the homotopy fiber of the natural transformation between the nth and the nth minus first term. You can think of this as perhaps a homotopical way of computing the difference between these two approximations. Part of Goodwillie's work shows that there's actually an equivalence of categories between these kinds of functors, which are now homogeneous degree n, so they don't have any lower degree part, just pure degree n part. And they can be characterized by something called a spectrum that has a sigma n, an action of the symmetric group, smashed with, if you're evaluating at at a object x, you're going to take an n-fold product of that space, and then you're going to divide out by the symmetric group action using homotopy orbits. And so, okay, if you squint, perhaps this looks like something I've erased. If you look at the nth term in a regular Taylor polynomial, you've got the derivative of your functor, your nth derivative of the functor times x to the n. And you can think of this as the part where you're dividing out by n factorial. So that's one example. The other example I want to look at is the one I'll focus on for the remainder of this talk. And this is the Abelian functor calculus. And now I'm going to switch to a more algebraic setting. So I'm going to look at functors from a category A to a category that I'll call B for the moment. I'll explain this. A and B in this context are Abelian categories. So in some sense, much, much closer to being in the world of undergraduate calculus. So we have a notion of a zero object, so an object that's terminal and coterminal. We have finite products. In fact, finite products equal finite coproducts. We have notions of kernels, co-kernels, and perhaps the strongest feature is that any morphism set in this category, so if I look at the morphisms between objects x and y in one of these categories, this has the structure of an abelian group. Okay, so category of abelian groups, of course, is an abelian category. Category of modules over a fixed ring, an abelian category. And the cha here refers to the category of chain complexes. In B. And what a chain complex is simply a sequence of objects in B and morphisms from B. Etc. Where these morphisms are required to have one essential property, and that is if you compose consecutive morphisms, the result is the zero morphism between those objects. And so this abelian categories, chain complexes, and abelian categories, this is the right context for thinking about homological algebra, which is where most of the functors from topological spaces to algebraic things wind up when you're in algebraic topology. And lost my notes. As with the previous example, maybe I can start economizing on writing here. This is a result due to myself and Randy McCarthy. It appeared in 2004. There's a functor calculus in this context in which PNF is, we'll say, of degree less than or equal to n. And of course, I now have to explain to you what I mean by that. So this notion of degree n is basically embedded in work of Eilenberg and MacLean. One way of describing this notion of degree n is to define something called a cross-effect functor. So as usual, F is going to stand for some functor on these categories, or I guess I'm saying chains, because I want to be thinking homologically eventually. The nth cross effect of such a functor is a functor in n variables and like I said, there are many ways to define this. I like to think of this recursively. So the zeroth cross effect of a functor is really just the constant part of the functor, the value of the functor at 0. If I'm interested in the first cross effect, if I take my functor f and evaluate it at an object A, because we're in this nice world of Abelian categories, there's actually a splitting. So this piece f of 0 sits in here as a summand. And if this functor isn't a constant functor, there's going to be some other part to it, which we call the first cross effect. And so on. So if I want to define the second cross effect and higher cross effects, what these are really trying to capture is the failure of a cross effect to be additive in one of its variables. So if I... Yes. Yeah, yeah. So yeah, in chain complexes, my coproduct is component-wise. Have this wrong. If I evaluate this first cross effect on a sum, again, the value of the first cross effect at A and B split off as direct summands. If this is an additive functor, then there's nothing else here. But if not, there's some remainder term, and that's what gets called the second cross effect. Okay? And in general, if I want to define the nth cross effect, I'm going to look at the failure of if I want to define the n plus first cross effect, I'm going to look at the failure of the nth cross effect to be additive in one of its variables. So we can split off this part and this part. If I'm additive in that variable, that's the end of the story. If not, the error term is the n plus first cross effect. Okay. These things are symmetric, so there's not an issue about which variable I'm picking here to define things. Okay. So I'll do an example, a simple example. So let's maybe fix an object in the category A, and let's just think about a functor from A to itself. If you want to think about this as going into chain complexes, think of it as a chain complex which has something in degree 0 and zeros elsewhere. And like I said, let's do something simple. Let's take the functor that assigns to input x the sum of x plus a. Okay, so if this is a sensible definition of degree 1 or degree n, the expectation is that this is degree 1. So let's check. If I follow this definition, the 0th cross effect for this functor is f of 0, which is a. If I try to compute f of a, I'm seeing, no, not f of a, f of x. Of course, that's x plus a. This part's my 0th cross effect. So this must be my first cross effect. And if I compute, say, the first cross effect of f at a sum, it's just x plus y, it's trivial. And the second cross effect is 0. And what I forgot to say is that this is supposed to give me a notion of degree n. I'm going to say that a functor f is degree n if its n plus first cross effect is trivial. Okay, so I think this example aligns more with our intuition. Question?
Yeah, can we treat the cross effect as a kind of the remainder of the Taylor series? If we would like to translate in terms of intuition about Taylor series, can we see it as a kind of remainder of the Taylor series?
Not clearly. Yeah. So what I'm not telling you is how these Taylor polynomials are constructed. So, yeah. Okay. So, I need to make a connection to Cartesian differential categories here. So let me talk about a couple of other results coming from this calculus. So again, this is, we'll call this a definition slash theorem. So this is in the same paper with Randy McCarthy. And in this paper, we defined a notion of directional derivative. So we can talk about the directional derivative of f as a functor. It's a functor of two variables. And you want to think of this as you do with directional derivatives. One of these represents a point that you're evaluating at, and the other is representing a direction. And there are a couple ways to define this. We can think about it as the linearization. So the D1 here means the same sort of thing it meant in the Goodwillie calculus, the difference between the first and 0th terms in the tower. And it's D1 of the functor f composed with this direct sum n functor, thought of as a functor of v. It's one way to think about it. If you want it to look maybe a little bit more like what you might see for a directional derivative in calculus, this is actually equivalent to doing something like taking the kernel of f of x plus v to f of x, where you're just looking at the projection from x plus v to x, and linearizing this. So think of this kind of like the difference you would see in a difference quotient definition for a derivative, and that being the limit of as t goes to 0 part. And so that's the definition part. The theorem is that there is a chain rule here. And the chain rule says if you have a pair of composable functors, the directional derivative of that composition is equivalent to the directional derivative of f with input consisting of the directional derivative of g and g itself. Okay? And I should mention, this is where Bjort starts making an appearance. So we proved this with a very weak notion of weak equivalence, quasi-isomorphism. Bjort upgraded this to a stronger notion of chain homotopy equivalence. Yeah. And so after several talks on differential, or at least one talk, after JS's talk on differential categories, Cartesian differential categories, you see this, and a natural question to ask is there a Cartesian differential category floating around in this picture somehow? But if you look at the date here, and you look at the dates on JS's slide, when we proved this, we certainly didn't know about Cartesian differential categories. I don't know if Robin did. The date, like the page, close, okay. So this wasn't on our radar screen, and it wasn't until this team formed that we actually thought about this question. Yeah. So with the time I have left, I'll say yes. The answer is yes. There is some sort of Cartesian differential category lurking in the background here, but there's some issues. There's some obstacles in the path. So I'm writing big and getting a workout with the boards here.
Just a quick check on the chain rule. F and G are composable, but I thought in this context we were looking at functors from A
To chain.
From B, so how do you compose?
So that would be one of the issues. Yeah, exactly. And I was deliberately vague there, yeah. Okay, so question, we're moving on to part 3. So the question you want to answer is there a Cartesian differential category where the differential operator is this directional derivative? And the big question is, what's the right category for this operator to act on? Okay. And there are really two fundamental issues that you have to address. I'll get to your issue in a moment. I'll take care of the easier one first. And that's this issue that I've kind of been alluding to throughout the talk. Everything I do is up to some sort of weak equivalence. Okay, so I didn't put an equal sign there. I put this little homotopic symbol. And so the first issue is that we're only working up to chain homotopy equivalence. So, and in particular, if you recall the definition of a Cartesian differential category, you needed a differential operator like this del, and it had to satisfy 7 axioms, which I won't repeat here. I'll quote JS. He said that the chain rule was arguably the most important. So this is a strong indication we have a Cartesian differential category. But the problem is that, again, Bjort, we can prove the chain, we can prove all the axioms for a CDC, but only up to chain homotopy equivalence. Okay, so everything but the chain rule and the symmetry action can be done up to isomorphism. But they're just, at least for the proof we have of the chain rule, there's just no way you're going to get an isomorphism. The other issue is this issue of composition. So I'll talk about the fix to this. This is actually an easy problem to fix. You just kind of find the right category and then take the homotopy category of that. And the other issue is also, I think, from a category theorist point of view, is maybe an easy fix, but was not initially obvious to me. Okay. So issue number 2 is composition of functors. Okay, and the issue is I keep talking about having, say, a functor f that goes from maybe C to chain complexes on B, and then I might want to compose that with a functor G that goes from, I'm getting my letters, let me at least get the letters lined up right here. I might have a functor G that goes from A to chain complexes on B, and there's a basic incompatibility here, okay? A first reaction might be, oh, well, you know, if you start by applying G, so you start with A, you apply your functor G, you get some sort of chain complex. F is only defined for objects in B, so maybe you just apply F to all the pieces in the chain complex. And the problem with that is I've not restricted F, and in particular, F isn't going to preserve 0. Or there's no guarantee of that. So even applying F degree-wise is not necessarily going to give me a chain complex, but what I can do instead is invoke an equivalence of categories due to Dalton-Kahn. So there's an equivalence category between the category of chain complexes on B and the category of simplicial objects in B. So this is just basically the category of functors from the opposite of the simplex category into B. And then it makes perfect sense to just post-compose an object in here, which is a functor from here to here, with my functor F. And that will give me now a simplicial object in the category of chain complexes on B, which of course is C, which is not really where I want this to land. But I can again, I call this dk. I can do this in reverse. So now I have, say, a category. Do it in reverse. Now I have a bicomplex. Still not what I want, but I know how to deal with that. If I have a bicomplex, so a chain complex of chain complexes, I can form something called the total complex of that. And that gets me back to where I want to be. And so, I mean, this is the notion of composition that we've been working with all along, and which, again, is natural from certain points of view. And yes?
So does it, if you translate chain C into C power delta up,
Yep.
does it correspond to some tensor on delta or something like that?
I don't know. Yeah.
Is this linked to taking chain complexes being some kind of monad? Which really looks like class decomposition. This really looks like a class decomposition.
Exactly. Yeah. So So like I said, to some people in the room, this is obviously a Kleisli construction. So there's actually, we can define Ch as a monad acting on the category abcat, whose objects are abelian categories. And whose morphisms have no hint of chain complexes about them, so they're just functors between A and B. I won't go into detail, but there's a comonad here, and if you do the Kleisli category, form the Kleisli category with respect to that comonad, that's exactly what we're doing here. Yeah. So,
It's a question of whether it's a monad or a comonad?
it's a monad. Yeah. Yeah. So this is the Kleisli category. Yes?
So I guess the functorial action of CH is given by the composition of dk and f star and dk minus 1.
Yeah. Yeah. Yes. Yeah. Yeah, we're up to isomorphism. Yeah. Okay, so I have just enough time for a punchline, right? So this is really, how you deal with issue number 2. How you deal with issue number 1 is you just take a homotopy category. So you're going to, in place of the morphisms that you would have in the Kleisli category, you're going to use chain homotopy equivalence classes of the morphisms. Okay, and so the punchline again from Bjort is if you take this category, which I'm not sure how you pronounce this, hoabcatch. If you sail, you think of a Hobie cat. I don't know if that resonates with anybody. But this category equipped with this directional derivative operator is a Cartesian differential category. Yeah, I'll stop here.
Thank you very much. Any questions or comments? Yes?
In the definition of functor calculus, you ask for Pn of f for every functor f. But is Pn functor also sometimes? I mean, if you have an
Yeah, you can think of it as a functor acting on this category of functors.
Oh, okay.
So
Okay,
yeah, so
nice.
I didn't mention that. Yeah.
Okay, cool.
Yeah.
If you don't take the homotopy category, this would be a differential category up to homotopy or something?
Something like that. So I mean, yeah, if you start kind of trying to make more connections between functor calculus and this world of differential categories, you start moving into higher categories. Yeah.
Okay, so I don't really have notions of homotopy, so it might be a very basic question, but do you have an intuition between what are chain complexes? Like what is it, or like drag it down to basic math? Especially why you need this this delta and the decomposition to be 0, for example.
That's an excellent question. It's, I mean, so from my point of view, this is, the composition being 0 means that for a chain complex, you can define what are called homology groups. So you take the kernel of one of these deltas, and you form a quotient with the image of the previous delta. And from the point of view of topology, things like homology of a space comes from first building a chain complex for that space. And that chain complex, in a very natural way, kind of measures n-dimensional holes in the space. I don't know if that helps. Maybe some other people in the room have a good answer to this.
It's not for answering that, it's to ask another question. So you constructed everything with this P of Pn, which abstract the idea of the Taylor polynomial. Is it possible to reformulate everything using instead the DNF, so like only the monomials? Like
no,
to make
so
all the constructions.
The way in which those DNFs get pieced together to form the functor is quite complicated. So it's not simply a matter of adding them together.
So it's not possible to reformulate all that you have told us, starting from the DN and then constructing the PN?
It's possible. This is not something I've worked on, but I'll mention a couple of people, Greg Arone and Michael Ching, have looked at how you can build the Taylor Tower from this kind of information. And there's, part of this involves having an operad structure for the derivatives, or the DNs, those coefficient terms for the identity functor, and then having an action of those operads on the derivatives of the functors you're trying to put together. And it's a very non-trivial process. Yeah. Maybe JS has, well, you've done something, you and Robin have done something looking at more taking the D1 piece of something analogous to the D1 piece and retrieving the Cartesian differential categories, but that's a slightly different question.
Any more questions? Well, if not, yes, there is one more question.
Okay, I've not followed everything, but do you use the cross effect to define the derivative? Because if you replace cross effect by the derivative, it gives you, you can define a polynomial of degree less than n like this.
So yeah, that kernel there is essentially a cross effect.
Okay.
And buried deep in the definition, in the definition of the Pn is that cross effect functor. It turns out it's part of an adjunction with and so out of that you get a comonad, and it's really the comonads associated to the cross effects that are used to build the PN Fs. Yeah.
Yeah, so I'm seeing that maybe there is also a link between functor calculus and differential characteristics and not Cartesian differential characteristics. Well, you have a monad.
I haven't.
I don't know.
Maybe we can talk a little bit about that. Yeah.
I don't know. No, JS.
So I just wanted to ask, so Goodwillie has a whole bunch of other calculators.
Yeah.
So could you say something about how well those are connected into differential worlds?
I don't know if anybody's made those connections yet. So I think that's a good.
To be done.
Yes, definitely. Yeah. I mean, Christine Bauer and Michael Ching and Matthew Burke have made the connection between, they have a notion of a tangent infinity category, that connects with Goodwillie's calculus of homotopy functors that I described. But as far as I know, there are other types of calculus that Goodwillie's played a role in developing called orthogonal calculus and manifold calculus, and I don't know if anybody's made those the connections with those yet.
Fantastic work to do. Let's thank our speaker again.
Thank you.